where we had wrapped up on Tuesday's class meeting was, I believe I had given you several different equivalent circuits. The ones that we are really going to use in this class are the cantilever equivalent circuits, and we stopped before we worked an example problem because all of our hands were getting tired from so much writing down of my bullshit. So let's what did I do with my notes? Let me find where I'm at in my notes and then we can go from there. Okay, this is a good spot. Put them in here backwards. All right. So let's say that we have a transformer and it is rated for 20 kilovolt amperes. One side of the windings, so the high voltage windings are rated for 8,000 volts RMS, and the low voltage windings are rated for 480 volts RMS. And it has the following resistances and reactances. So let's say that RP is equal to 32 ohms, RS is equal to 50 milliohms, RC is equal to 250 kiloohms, XP is 45 ohms, XS is equal to 60 milliohms, and XM is equal to 30 kiloohms. So before we even get into anything here, I want to ask you guys a kind of a conceptual question, okay? Why do you think the secondary resistance and the secondary reactance are so much smaller than the what I have labeled as the primary resistance and the primary reactance? Exactly right. So the 8,000 volt RMS winding is going to have a whole lot more turns because it's the higher voltage winding. And the 480 volt RMS winding is going to have significantly fewer turns because it's at a lower voltage. So if we have less windings, we're using less wire, our coil has less inductance. So it makes perfect sense that the resistance of that secondary winding and the reactance of that secondary winding should be appreciably smaller than the primary side or the high voltage side. Okay, great job. All right. So let's answer a few questions here, okay? And I might append to this as we go along, okay? So the first thing that I would want us to do is to determine the equivalent circuit for the transformer with all impedances referred to the high voltage side of the transformer. Okay. So let's do this first, and then we will move along to the other things, all right? So I'm going to start by drawing the model of the whole thing, okay? So that's going to look something like this based on the parameters that we were given. So here's our voltage V1. Here's where RP would go. So this is 32 ohms. Here's where XP would go. So this is going to be J 45 ohms. Here is our core resistance, 250 kilo ohms. Our magnetizing reactance, sorry, that should be drawn as more of a coil. Grand scheme of things, it wouldn't matter too much. This is going to be J 30 kilo ohms. I'm going to put N1 here and N2 here. Here's RS, so this would be 50 milliohm. Here's J 60 milliohm. And then here's where our secondary voltage would be. And then for what it's worth, here's where the current I1 would be if this was connected. And this is where the current I2 would be, again, if this side were connected to anything. So this is what my equivalent circuit model looks like prior to me doing any referring or reflecting things around, right? So before we do any of that referring or reflecting, we need to figure out what our turns ratio is, okay? So hopefully we all remember that our turns ratio A, as far as we're concerned in this class, is N2 over N1, but I didn't specifically give you those number of turns in each coil. Instead, I gave you the voltages, but luckily enough for us, the ratio of the voltages, V2 to V1, is also going to be our turns ratio.
I mean, can't you just always think of it as the ratio, so it doesn't matter what number you give to it? Except unless you give us the currents, which is opposite.
Right. No, pretty much, yeah. That's pretty spot on. So if we're going to refer everything to the high voltage side, so I'm going to make a note over here because we're not being quite specific enough. The high voltage side is going to be the primary, and the low voltage side we're going to consider to be the secondary in this case. Okay.
But that won't always be the case.
No, because so if we have this particular configuration, we would be using this transformer as what's called a step down transformer because we're converting our 8,000 volts rated on one side down to 480 volts on the other side.
We're going.
But if we wanted a step up transformer, then we would consider the low voltage side to be our primary and the high voltage side to be our secondary, right? So I'm telling us very specifically here, we're going to use this guy as if it were a step down transformer, okay? So that means that we are going to have a ratio of 480 volts RMS to 8,000 volts RMS. We could leave it as 480 over 8,000. I'm going to simplify it slightly just for math's sake. That looks like 3 over 50. Okay. So We can either choose to do this. So we've got everything in our normal equivalent circuit. We could refer things over, or we could decide that we want to work with a cantilever equivalent circuit, okay? So I say, let's work with a cantilever equivalent circuit where everything is referred to the primary side, or excuse me, the high voltage side, because that's the one that's going to be easier for us to use if we wanted to do any subsequent analysis on, how much power was delivered to a load or something like that. Okay. So finding cantilever equivalent circuit referred to the high voltage side, okay? So what would the total series resistance be if we were referring everything to the high voltage side?
32.05 plus.
Where the hell did you get 0.05? Oh, okay, so no, all right, so I see where he got the 0.05. So the 0.05 is from the 50 milliohms. Okay, so, but it's not gonna be 32.05, okay? So the 32 ohms is already on the primary side, so we don't need to scale that by any factor whatsoever.
Okay.
That 50 milliohms, though, is going to have to get scaled by a factor of 1 over A squared, right?
Oh,
So we're going to have 50 milliohms over A squared, which is 3 over 50 squared. So let's throw this in our calculators real quick. And see what shakes out of this. Okay. So we only need to refer the secondary impedances over to the primary side because the primary impedances are already on the primary side, or the high voltage side in this particular case, right? So 32 plus 0.05 divided by 3 over 50 quantity squared comes out to be, when I did it, 45.889 ohms. So we can see that 50 milliohms of resistance when referred to the primary side looks like about 13.9 ohms. Okay. What are we going to do for our, so this should be REQP because we referred it to the primary. My apologies. So what are we going to do for our reactants, our series reactants? You would be correct. It's literally that easy, right? So we're going to start with XP by itself, 45 ohms. And then we are going to refer that 60 milliohms of reactance over by dividing it by A squared. And so that's going to come out to be 45 plus 0.06 over 3 over 50 squared. And I get that to be 61.667 ohms. Okay. Do we need to do anything to our core resistance of 250 kiloohms? No, because it's already on the primary side. Do we need to do anything to our magnetizing reactance? No, because it's already on the primary side. So putting these pieces of information together, our cantilever equivalent circuit would simply be this guy right here. So here's V1. They will once I actually draw them in, but I was only looking at the reactances. So up here, when I had all of my inductances, I put the J. When I'm doing the math, I don't need to worry about the J. I'm just going to tack that on at the end. So 250 kiloohms, J 30 kiloohms. $45.889 ohms. J 61.667 ohms. And the voltage on this side is going to be V2 over A. For what it's worth, the current flowing in here, I1, current flowing out of here, if this thing were connected to something, would be A times I2. So that seems fairly straightforward, right? If we wanted to, so I'm going to make a note out here. Cantilever equivalent circuit, high voltage side. If we wanted to find the cantilever equivalent circuit referred to the low voltage side, so let's do that as part B, right? We've answered part A there. So find equivalent circuit referred to the low voltage side, all right? So we can follow a fairly similar process, but it's going to be slightly more involved, right? So the first thing we might be interested in would be the series equivalent resistance. So let's call this REQS or refer to the secondary side. So Zach, I'm going to let you kind of redeem yourself here. How would we do this guy?
Well, we take 32 ohms and we
So when we referred from the secondary to the primary, we divided by A squared.
all right, so we
So,
multiply.
so we're going to multiply by A squared to go from the primary to the secondary. Absolutely right.
Good.
So that's going to be 3 over 50 quantity squared. What are we going to do with our secondary resistance?
Oh, wait.
Nothing. It's already on the secondary side.
Second.
Yep. So throwing this into the calculator, 32 times 3 over 50 quantity squared plus 0.05. I wound up getting 165.2 milliohms. So for the reactants, we'll do something similar here. So that's going to be 45 times 3 over 50 quantity squared plus 60 milliohms. Which I get to be 222 milliohms. Now let's worry about the core resistance referred to the secondary side. So that's why I'm calling it RCS now. So this is our secondary, referred to the secondary side. So we're just going to treat it as if it were just a resistance, right? Because that's all it is. So that's going to be 250 kiloohms times 3 over 50 squared. And that comes out to be 900 ohms. And then lastly, we have our magnetizing reactance referred to the secondary side. So that's going to be 30 kilo ohms times that quantity 3/50 squared. Comes out to be 108 ohms. Putting these pieces together, our secondary or low voltage cantilever equivalent circuit would look something like this. So let's put my resistance here of 165.2 milliohms. My reactance of 222 milliohms. Here is my 900 ohms of reflected core resistance. Here's my J 108 ohms of reflected magnetized reactance. And then we're going to have our voltage V2 over here, our current I2 over here. This guy should be AV1. And this guy should be I1 over A. So just as a quick heads up, cantilever equivalent circuit, low voltage side. Okay. All right, so let's use these equivalent circuits to do something, okay? So let's do just that, okay? So part C, let's say that we will assume this transformer is supplying a rated load at 480 volts RMS. So that is the measured voltage across our secondary terminals at a power factor. Did I hear a groan? PF is equal to 0.8 lagging, okay? What is the transformer's input voltage V1? And we're just going to worry about the magnitude. Okay.
You got like I remember what them.
Okay. All right.
One side, I don't either real or imaginary.
Okay, so let's start by seeing if we can glean some information about our load from this statement, okay? So this is stuff I asked you guys to do back in 280 last spring. I absolutely understand it's been at least 6 months since you did it, and it's been an infinite amount of time since you gave a shit about it because you never did it, but that's okay. So how, anybody remember how we might calculate the complex power absorbed by our load?
Okay, so, no, wait, it's just, it's just voltage over, not over.
So let's start with what is the complex power in general, okay? So complex power, we have two options, right? We could do it in rectangular form where we have average power plus J reactive power, or we could do it in polar form where we have apparent power, angle, power factor angle, okay? So let's deal with polar form here because we already have a lot of that information, okay? So if this transformer is supplying a rated load, our power that's delivered to the load is 20 kilovolt amperes because that is the power rating of this guy, okay? That is an apparent power rating. So our apparent power is 20 kVA. Okay. Our angle is going to be the inverse cosine of our power factor. And I heard you guys talking about this because our power factor is lagging, we should expect that angle to be positive, which means we're going to put a little positive sign in front of there to force that to happen, okay? So when I throw this into my calculator, I'm going to get 20 angle inverse cosine of 0.8.
Yeah, how do you get there?
God damn it.
God damn it. What? You gotta be complex.
You are in complex.
Ah, here we go.
It's a little over 6 months, we forget how to live.
A lot has happened. I would say, listen, I lost my TI 36 extra with that time, so I can't even do it.
All right, 20,000 equal 36.8.
You almost killed Zach. You almost killed him.
I got a syntax error.
Yeah, am I?
How do you switch it to angle? I'm getting.
You press this little format button down here.
Yeah.
All right, then you're just
Right.
inferior
At least like that.
to my calculator. My calculator is better than that. CXCR.
I have to figure out what I
My
did.
calculator is smarter than
Anybody else need help remembering how their calculator works? You a complex mode?
I do a Texas Instrument.
Yeah.
I do be working at Open.
I know, that's from like.
Oh.
So there you go. That, so I'm good. Now I do your level, I try it.
Yes. First. Oh, eight.
This is why we're a Casio family, okay? You see, these two are the reasons that I'm be a Casio.
Oh, I'm catching. What the fuck is wrong?
Casio family in the house.
Yeah.
Specifically,
No, I got it.
this one's beautiful. This calculator is beautiful. Yeah. This is the one that me and Charlie went bought. During the beginning of creating.
I remember when that happened. No, I got it, I missed it. Oh my God.
Hey,
How is my TI 30 and I fucking ate it?
Yeah.
I got the level with the orange button and that.
All right, so
Because I had lost my first one.
let's, get back to things before you guys argue about the merits of calculators for the next hour and a half. Which I can, yeah, but anyway, okay. So now that we know this complex power, I'm gonna ask you another question that is gonna piss you off even more. How might we go from knowing this quantity to knowing the impedance of the load?
Wait.
So the impedance of our load, Z load, is going to be the magnitude of the voltage drop across our load
Oh, that's bad, man. Get the fuck out of here.
squared divided by the conjugate of our complex power. I know you guys are having flashbacks and all kinds of terrible things, okay? Just to remind you all, you can have your calculator do the conjugate operation for you, but it is not that bad, okay? So what is the voltage drop across our load? The magnitude of the voltage drop across our load according to our problem statement. 480 volts RMS, right? We are told we have a load drawing rated power at 480 volts RMS, okay? So 480 volts RMS, quantity squared. And then here in the denominator, the conjugate of our complex power absorbed by our load is going to be 20 angle negative 36.870 kilovolt amperes, okay? So when I put this in my calculator, I'm going to do 20,000 angle negative 36.870 so that my answer will come out to be in ohms, okay? So 480 squared divided by 1,000 times the conjugate of my previous answer. 20 times 1,000 is 20,000.
Okay.
I'm just having my calculator do the work for me because I'm lazy. I wind up getting an impedance in polar form of 11.52 with an angle of 36.87 degrees ohms, or in rectangular form, this is 9.216 plus J 6.912 ohms. So I'll give you guys a moment for those of you that desperately need to practice using your calculators to do this thing.
Being this calculator, it's like riding a bike. I love this thing. Oh my god.
Yes, Nick.
You don't have to do it in those, or if anything, you can have class. Kind of like do a refresh, like with polar and that other one, like which half means what.
Sure, I can do that here really quickly. Let me just jump back to page 10 here. Caleb.
You said before that we were gonna keep the angle positive on the 20 angle 36.87, so, but it was negative on the.
I'll get back to that in just a second, okay? So just as a very, very quick crash course, let's start with impedance. In polar form, we have magnitude of impedance and then the angle of the impedance, right? So this magnitude of the impedance right here is literally just the magnitude of the voltage divided by the magnitude of the current. Theta Z is the angle of the voltage minus the angle of the current. Okay. In rectangular form, this is usually expressed as R plus JX, where this is our resistance measured in ohms, and this is our reactance measured in ohms. So in this class, we have actually been using X, the reactance, instead of bothering with inductance and things like that. We've been just using the reactance outright, which is why I've been having all of those things where we have resistance and then a JX term, okay? So that's a more common thing to do in power engineering than just bothering with the actual value of inductances and stuff like that. Because when you're working at a fixed frequency, the value of the inductance literally doesn't matter. The reactance is going to be the same, okay? So those are the different parts of impedance, okay? For complex power, our generic equation is just our RMS phasor voltage times the complex conjugate of the current. I'm going to hit you guys with some alternative relationships here in a moment. But before we do that, this is a complex number. So it can be expressed in polar form, where we would have the magnitude of our complex power, commonly known as apparent power, measured in volt amperes, just volt amperes, excuse me. Angle theta s, where this is our power factor angle. And I'm going to make a sub note here in a different color. Positive angle means lagging. Negative angle means leading. Heard you guys discussing that. Absolutely right. We will be using those relationships, so I'm just bringing them back to your attention. Okay. In rectangular form, our complex power can be split up into our average power, measured in watts, plus J times Q, where Q is our reactive power, measured in volt amperes reactive. Now, some alternative relationships that we might use, and we actually literally just used one of them, is that we can also say that complex power is the magnitude of the voltage squared divided by the conjugate of a known impedance, or it is the magnitude of an RMS phasor current squared times the impedance itself. We don't need to do the conjugate operation. Okay. So to answer Caleb's question from a moment ago, okay, the reason why I wound up putting a negative angle, even though I said that we would have a positive angle, and I'll explain where that differentiation came from. If we took that relationship, S is equal to the magnitude of the voltage squared divided by the conjugate of the impedance, and we rearranged it so that we wanted to find the impedance itself, right? So if we algebraically manipulate this guy, effectively we could just switch where we have S and switch where we have Z, okay? So if we multiply both sides by Z conjugate and we divide both sides by S, we're going to wind up getting Z conjugate is equal to the magnitude of the voltage squared divided by S. Well, now I could take the conjugate of both sides in order to get just Z by itself. Well, if I conjugate Z and then conjugate it again, I just undid the conjugate. So I'm going to erase that conjugate there. The conjugate of the magnitude of the voltage squared is going to be the voltage, the magnitude of the voltage squared, because it's a real term, so the conjugate doesn't do anything. The only thing that's actually going to get conjugated is that power. So that's why I wound up switching the sign on the angle of the power for that particular calculation, because I needed to do the conjugate.
Makes sense.
Okay.
There be a reason to conjugate in rectangle? We just do it for multiplying the value.
So there could be a reason to conjugate in rectangular. So let's talk about what that entails just really quickly, okay? So more review. So if I have a complex number A that is expressed in polar form as the magnitude of A with an angle theta A, and in rectangular form as lowercase a plus JB, where lowercase a is the real part of complex number capital A, and lowercase b is the imaginary part of complex number capital A. The conjugate of A is going to be in polar form the magnitude of A with an angle of negative A. And in rectangular form, it is going to be lowercase a minus j lowercase b. So the conjugate operation on a polar number switches the sign on the angle. On a rectangular number, it just switches the sign on the imaginary part. That's it. Any other complex number, impedance, or complex power related questions, topics, or whatever that need to have a quick review? Are we good to?
Find divide. Got like what the exact operation.
Do you genuinely want to know that, or are you just trying to waste my time?
No, I don't.
That's a question for Matthew.
So realistically,
Divide the, multiply the first number and then subtract or add the angle.
okay,
No,
so
that's only, that's for rectangular, for polar, for sure, you use multiply.
God damn it. Okay. I would put, so the short answer would be just put it in your calculator because it doesn't give a shit whether you're in polar or. Yeah. So just as a really, really quick thing. Oh, damn. Division, okay?
So we're taking the test what, February 27th?
I don't know if you should ever have the
That's how it works in polar form. This is the easier way to do it by far. In rectangular form, if we had A is equal to A plus JB and B is equal to C plus JD, then we would have to do A times the complex conjugate of B over B times the complex conjugate of B in order to get rid of the imaginary part of our denominator. And so that's going to wind up looking like A plus JB times C minus JD all over C plus JD times C minus JD. So this comes out to be a denominator of C squared plus D squared. And then up here, we're going to have AC plus BD plus J BC minus AD, I believe.
Looks like I'm putting that in my calculator.
Rectangular form division is pretty damn difficult, so that's why you have
So
calculators.
what you're saying is don't ever try and do this by hand, just put it.
All right, so let's get back to the problem that we were working before we got distracted.
Tired of the problem that's on the way.
All right, so I'm going to redraw my circuit now, okay? Including my load. So I'm going to give you guys the question of, do we want to draw our circuit with everything referred, our total circuit with everything referred to the primary side, which we already have a cantilever equivalent circuit for, or everything on the secondary side? So I would argue that right now, the easiest path would actually be with everything on the secondary side, because our load is connected to the secondary side, so we don't need to transform that as well, okay? So a low voltage equivalent circuit, including our load, would look something, and our source that we're trying to find would look something like this, okay? So here is our voltage source. We're trying to figure out what it is. Hold on, let me look at what I did here. So I'm going to do something here. I did this slightly differently in my original notes for this. So realistically, all I'm going to do, I'm going to take this guy right here and move it to the left-hand side of my impedance, just so that my two cantilever equivalent circuits effectively look like the exact same thing, okay? So you might be saying to yourself, well, why the hell is he bothering to do that? And the answer will be a little bit more obvious here in just a second, okay? So this is my transformer equivalent circuit. This is my secondary referred transformer equivalent circuit. So let me just scroll back up here real quick. So this is 100, no, excuse me, this is 900. And then J108. This guy right here was 165.2 milliohms. This guy was J222 milliohms. There's the secondary terminals of my transformer. And now I have my load impedance, which we just found was 9.216 plus J 6.912 ohms. What we're trying to find, let me just scooch this 900 over, my apologies, is the voltage for our source, which would be V1, excuse me, A times V1. Okay. And we know that this guy right here is 480 volts RMS. So how might we figure out what A times V1 is, and then from that figure out what V1 actually is, which would be our input source voltage on the primary side or the high voltage side of our transformer.
Think our 350, multiplied by 8,000. But we're talking about V1.
We're trying to figure out what V1 is.
So wouldn't V1 be 8,000?
It won't be. It won't be exactly 8,000. It'll be something pretty close to 8,000. So the reason why I'm saying it won't be exactly 8,000 is because we have a practical transformer, right? So there are going to be some losses in our winding resistance and stuff like that, because there's going to be current flowing through it. And so there's going to be a voltage drop across it and things like that. So if this were an ideal transformer, yes, the answer would be 8,000. We wouldn't have needed to do literally any of this shit, but it's not an ideal transformer, okay? So it's going to be something pretty close to 8,000 probably, but it won't be exactly. So there are a couple of different ways that we can do this, but this is the reason why we use a cantilever equivalent circuit, okay? So with a cantilever equivalent circuit, I have these guys that I can lump together as one impedance. And then I have this guy right here that is a single impedance. So I have just two impedances in series. I know the voltage drop over one of them. So can I use something like, I don't know, voltage division to find out what the total voltage across that series combination of impedances is? I think I can. Yeah, right? So we could say, using voltage division, not having to bother with finding currents all over the place, this, that, and the other, that our voltage A times V1 is just going to be, actually, let me write that this way. We know that 480 volts RMS is A V1 times our load impedance 9.216 plus J 6.912 ohms divided by our series transformer impedance 0.1652 plus J 0.222 ohms plus our load impedance of 9.216 plus J 6.912 ohms. And so from this, we could say that V1 is just going to be 480 volts RMS divided by A multiplied by the reciprocal of that resistance ratio or impedance ratio. So 0.1652 plus J 0.222 plus 9.216 plus J 6.912 ohms. All over 9.216 plus J 6.912 ohms. And for what it's worth, I'm just going to replace this A really quickly with a 3/50. So when I throw this thing into my calculator, 480 over 3/50. Press the fraction button. There we go. 0.1652 plus 0.222 I plus 9.216 plus 6.912 I over 9.216 plus 6.912 I wound up getting a voltage of 8,184.459 with an angle of 0.381 degrees volts RMS. So this is the magnitude of V1 that we were looking for. So it's something close to 8,000, but it isn't 8,000 because those practical impedances will have some voltage drop over them. Now, more realistically, we probably would wind up working a circuit when we were analyzing something in a more traditional sense, the other way around, right? We would more likely have access to know what the voltage provided by our supply is, and we would want to know maybe how much complex power or something like that is absorbed by a particular load. So let's do that, okay? So let's say, as part D, and this will be the last part of this problem, that we have an induction motor whose impedance is, let's say, 8 plus J3 ohms, okay? What will the average power delivered to the motor B. If a voltage of let's say Vs is equal to 8,000 volts RMS, angle 0 degrees. So this is voltage applied at the high voltage side of the transformer. Okay. So for this particular problem, I want to use the cantilever equivalent circuit that was referred to the high voltage side. So one thing that I'm going to need to do to facilitate this is reflect my motor's impedance over to the high voltage side. Okay. So let's say that Z motor P for primary impedance. How would we do that? Divide by A squared. Absolutely right. So this is going to be 10 plus J3 ohms over 3 over 50 quantity squared. So this comes out to be 2,777.778 plus J 833.333 ohms. Okay. So my new circuit that is describing what's going on here would be something like this. So I have 8 kilovolts. I only do 8 angle 0 kilovolts RMS. Here's my primary side of my transformer. So here's V1. Doing my little $250 kilo ohms, J 30 kilo ohms. And scroll back up here real quick so I can remember what these guys were. 45.889 J 61.667. What was that, Brock? 30. All right, so this is our circuit. For what it's worth, the voltage here is going to be V2 over A. The current entering is going to be A times I2. Here's I1. We don't really need literally any of those things here, though. Once we reflect this impedance over, this is just a simple circuit for us to analyze. So if I were interested in finding the power, let's say complex power, just for the sake of argument, and because once we know the complex power, we can very easily find the average power, which is what we're looking for. I really only need to know either the voltage drop across that reflected load, or the current flowing through that reflected load, right? So I'm going to find the current flowing through the reflected load. Okay. So I'm just going to call this IL for I load. I'm not going to worry about the fact that it's AI2 or anything like that, because I don't really care what my actual secondary current is, nor do I actually care what my secondary voltage is. I'm just interested in the power in this case, okay? So just using nothing more than good old-fashioned Ohm's law, I believe that we should have a voltage of 8,000 angle 0 degrees volts RMS in our numerator. And then in our denominator, we would have 45.889 ohms plus J 61.667 ohms plus 2,777.778 plus J 833.333 ohms here. And when I throw this into my calculator, give me a moment to do that, please. I got a current of 2.7007. So let's call this 2.701 with an angle of negative 17.587 degrees. Amps. So knowing that current, I can find my complex power by simply taking the magnitude of my load current squared and multiplying it by my load impedance, which in this case is that Z motor P. So this would be 2.701 amps RMS quantity squared times that 2777.778 plus J 833.333 ohms, which would give me a complex power of 21,157.285 with an angle of 16.699 degrees volt amperes. So we're actually a little bit beyond a fully loaded motor here. So wouldn't be safe to operate it in this fashion for an incredibly long time, but for short durations, it's not so overloaded that it's going to cause anything to burn out or anything like that. And expressed in rectangular form, this looks like 20,265.004 plus J 6,079.498 volt amperes. So what's the average power? Yes.
What makes you say it's overloaded?
21,157 is larger than 20,000. It's rated.
20,000.
Yeah, it was rated for 20 kVA. We are pushing 21.1 kVA through it, so it is slightly overloaded. It was literally the first thing that you were told. It was indeed a long time ago. No, that was the first character. But anyway. So circling back around so that we can keep us kind of on track. What's the average power? 20,265 in watts. So that particular motor is drawing about 20 kW.
Thank you for not filming this one.
Yeah, I don't know. So, I mean, I added a couple of parts to the example because I wanted to show you how this would be used, but yeah.
I think we would have actually just like all charged you at once.
All right, so we have worked a heck of an example here. We've spent a lot of time figuring out how to use these things. Let's get back to something else, okay? So I'm going to talk about where these equivalent circuit parameters come from. And for what it's worth, in you guys' lab class next quarter, you are literally going to be doing these experiments, okay? So this is going to be called determining equivalent circuit parameters. And this also ties in a little bit with some of the stuff we learned towards the end of 280, in as much as these calculations involve the use of watt meters, which we talked about as how we measure power in AC systems and all that kind of good stuff, okay? So in order for us to determine our equivalent circuit parameters for any practical transformer, we carry out two tests, okay? We have an open circuit test and a short circuit test. So we're going to talk about the open circuit test first. Yes. Okay. So I'm going to draw a picture for the open circuit test here, okay? And then we'll kind of talk our way through it. So I'm going to start with my voltage source, okay? So we are going to apply rated voltage across typically the high voltage windings, okay? Doesn't necessarily have to be the high voltage windings, but it is typically the high voltage windings of our transformer, okay? The next thing that I am going to draw is our effectively the measurement circuitry that's going on here, okay? So we are going to have a voltmeter and so this is going to tell us the magnitude of some AC voltage. Really, it's telling us just the magnitude of the voltage that we are applying to this thing. We are going to have an ammeter, which is telling us the magnitude of the current. And then over here to the right, we are going to have our watt meter. Where I'm just labeling the positive polarities of the coils. I'm going to draw kind of a little box around this guy, just so that you know this isn't really circuit elements. This is just representing how the watt meter is connected, which we discussed in our last class meeting, or excuse me, in 280. And so this is going to be giving us the open circuit power. Okay. So this is our measurement thing. And then we are going to connect this to our practical transformer, which I'm just going to represent by a simple transformer signal symbol here, with, so I'm going to make a note here. This is typically the high voltage winding, okay? So that's where all of our measurement stuff is applied, is connected to the high voltage winding. Our rated voltage is applied to the high voltage winding. Our low voltage winding is over here, and we are literally going to leave it open circuited. The reason why we leave it open circuited is because this is an open circuit test. So that is what's open circuited, okay? So now let's talk a little bit about why this works, okay? And what parameters we're going to be able to get from this. And so I'm going to do that by drawing my cantilever equivalent circuit with everything referred over to the high voltage side, okay? So this measurement circuit looks like this thing. Another one, yep.
I think I took a picture of the first one.
So here is that voltage VAC that's measured by our voltmeter. Here's that current IAC that's measured by our ammeter. And then now I'm going to connect my transformer equivalent circuit over here on this side really quickly. And so here we have RC, here we have JXM, here we have REQP, and here we have, excuse me, that should be a coil, JXEQP, and then open circuited. So just intuitively here, we'll talk about the math behind it in a moment. What parameters do you think the open circuit test helps us figure out? Something is correct. Could you be slightly more specific, please? So let me ask you guys what I hope to God is an easy question. How much current is going to flow through REQP and JEQP in this system? Exactly right. So the reason why we leave the secondary or the low voltage windings of our transformer open is to make sure that none of our current will flow through those series component. Everything is through the shunt or the parallel things. So quite obviously, I hope the open circuit test is going to give us the information that tells us what RC and XM are, because they're the only parts of our transformer that are effectively being energized in this system, okay? So since all of that AC current is going to flow through our shunt impedances, we can say that in general, our open circuit test impedance, ZOC, is going to be whatever our AC voltage is divided by our AC current is. And this is going to look like just RC in parallel with JXM. And so I'm going to write that as RC times JXM over RC plus JXM. And using complex math that I'm not going to make you guys do or even bother with, from this, we'll find that RC is simply the ratio of our measured open circuit voltage from our test squared divided by the power measured by our wattmeter. And XM is going to be 1 over the square root of IAC over VAC. Those are just magnitudes, so these are just things that we can literally measure. squared minus 1 over RC squared. All of this is underneath the square root sign. So literally those three measurement tools, our voltmeter, our ammeter, and our wattmeter, the readings on those during from the open circuit test, we can extrapolate what our our core resistance is and what our magnetizing reactance is. In a similar style of process, we also have a short circuit test. Okay. Where in our short circuit test, generally speaking, we apply a reduced voltage across our high voltage windings and wind up short circuiting our low voltage windings. Okay, we don't have to do it that way, but typically it is how it's done. So I'm going to draw a picture kind of depicting this as well. Okay. And then I'm going to follow it up with a picture of what the circuits, what's actually going on in the circuit stack. So be ready to be pissed off. You're drawing two more things.
That's okay, I'll take pictures.
So this is our, I'm just labeling it as a reduced voltage, okay? So the idea here is we apply a reduced voltage such that we're only going to wind up having rated current flowing in our secondary so that we don't burn out anything, okay? And we need to lower our voltage because our load is effectively zero, okay? So we've got our reduced voltage being applied here. Then we've got our measurement circuitry. Once again, this consists of a meter measuring some magnitude of an AC voltage, an ammeter measuring some magnitude of an AC current, a wattmeter here measuring some, I'm going to call this PSC for short circuit power. I'll draw a box around this guy yet again for our wattmeter. And then we actually have our connection to our transformer finally over here. And I'm just going to depict this as just the schematic symbol of a transformer for right now, where this is our high voltage windings yet again. This is our low voltage winding. And then we short circuit these guys such that rated current is flowing in our low voltage windings. Yes. So when I draw my equivalent circuit, you're absolutely correct. What we're going to see is that essentially all of our current is going to wind up flowing through our short, and it's also going to flow through just our series elements, okay? So I'm going to draw this as if everything were referred over to the secondary side here really quickly, right? So that might look like something like this. So here's our AC voltage. Here's our AC current. Here's our REQ secondary, our JXEQ secondary. RC secondary, JXM secondary, and then here's our short, where we have our rated current flowing. Okay. So by drawing the circuit like this, it's hopefully pretty obvious to see that all of the current that is effectively injected into our system by applying that lowered or reduced voltage, excuse me, flows only through the series portion, and it bypasses the parallel portion. So, Brock. So that's a fantastic question. So Brock asked how it is that we're able to just move that parallel portion from the left or to the from the left side of those series impedances or the right side of those series impedances, whichever makes it convenient for me. Fantastic question. The answer to that is the impedance of that shunt part or that parallel part are literally hundreds, if not thousands of times larger than the series part, even if it doesn't matter if they're referred to the primary side or the secondary side. So we know that almost no current is going to branch off and flow through them. So it really doesn't matter which side we put them on. There's going to be inaccuracies regardless because we're using a cantilever equivalent circuit. So the cantilever equivalent circuit is making that correct assumption that practically no current will branch off and flow through that shunt branch. So that's why we can lump the series bits from both the primary and secondary sides together. So we're already making an assumption and introducing some error to begin with. That assumption also happens to allow us to move that shunt branch to the left side of the impedance or the right side of the impedance, whichever one makes it convenient. If we didn't make that assumption, we could still do the circuit analysis, and in technically speaking, it would be much more accurate. I say much more accurate. We're only going to be introducing around 1% error anyway, but the amount of analysis and math needed to do it would be much more difficult, because we would effectively have a situation where we would need to be applying mesh analysis or nodal analysis to an AC system, as opposed to simple things like voltage division and Ohm's law. So we're introducing this error intentionally, as it were, to make the math easier. But that's a very, very good question. The magnitude of those impedances are so large that they look almost like open circuits when we're only considering the series paths. Yeah. All right, so our short circuit impedance will be the ratio of that AC voltage to that AC current, which is going to be then just REQS plus JXEQS, where, again, I'm not going to make you guys suffer through things. REQ is going to be the short circuit power. Sorry, my handwriting in my notes is so small. I keep reading that as an A when it's supposed to be a C. So PSC over the magnitude of our AC current squared. And XEQ is going to be the square root of the magnitude of our voltage divided by the magnitude of our current. Sorry, that line should be straighter. My apologies. Quantity squared minus REQ squared. Now, you may have noticed here that I took off the subscript S from this REQ calculation and this XEQ calculation. And realistically, well, those guys are inherently kind of on the primary side. RC and XM are always thought of to be on the primary side normally, okay? The reason why I did that is because sometimes when you get the results of these tests, they will have everything referred to the high voltage side or everything referred to the low voltage side, but the equations still work. So as long as the power is also referred to the high voltage side or the low voltage side, everything's going to be okay. So I took those subscripts out to make them more generic. So as one last example for today, before I stop your suffering for just today. I feel like I'm missing a page of notes here. Oh well. Yeah, it's fine. Doesn't matter. I don't feel like I'm actually missing anything in the notes, just things are numbered differently. So let's look at a quick kind of like a results of a test or something like that, okay? So let's say that we have a 50 kilovolt ampere rated 2400 to 240 volt RMS transformer. And I'm going to specifically say 60 hertz here, even though I don't think we need to use the frequency for anything. Is tested with the results shown below. So I'm going to put my open circuit test results here. My short circuit test results over here. And I'm going to actually make a note that the open circuit tests were done on the low voltage side. And the short circuit tests were done on the high voltage side. So you can do them on either side. Typically, the reason why we do, so like one reason why you might want to do an open circuit test on the low voltage side is that maybe your lab or whatever that is doing this testing, like, I don't know, the one we have over in Nefkin, doesn't have access to thousands of volts RMS. We might only have access to, let's say, 208 volts RMS at a max or something like that, right? So we might do the open circuit test on the low voltage side because that's the voltage that we happen to have available. Still going to work out okay. Just all of our parameters will be low voltage side parameters. Similarly, we might do our short circuit test on the high voltage side for effectively the same reason. If we do our short circuit test on the high voltage side, the amount of current that's going to be flowing through that high voltage winding will be the rated current through the high voltage winding is going to be much less than the rated current for the low voltage winding. And we might only be able to inject a small amount of current. Okay, so we can do them on either side, but I described the traditional way of doing it if you were in a lab set up for doing those tests, like at a transformer manufacturing facility, like the one we have over here in Shreveport, Bossier. Over here on the left, I'm going to put the measurement device, and then I'll give you the results of the test. All right, so let's say that our voltmeter measured an open circuit voltage, VOC, of 240 volts RMS, which should make sense because that is the rated low voltage. And for the open circuit thing, we apply rated voltage. Our ammeter, what was that, Zach? Or sorry, that wasn't Zach.
Is that an A or a C?
Or A or an O?
This is an O because I'm calling it an open circuit voltage. Right. This is going to be IOC, so this is just the result of the open circuit test. And let's say that this was 6.50 amps RMS. And lastly, for our watt meter, we have our open circuit power was measured to be 65 watts. Okay. For our short circuit test, I'm going to call this voltage over here VSC. So this is just the voltage from our short circuit test, was 45 volts RMS. Our short circuit current was 20.833 amps RMS. And our short circuit power was 300 watts. And I want us to use this information to determine the primary referred cantilever, or let me, instead of calling it primary referred, let's do high voltage referred cantilever equivalent circuit. Okay, so let's start with the results of our open circuit test first, okay? So the core resistance referred to the low voltage side. We go back to our relationships up here, is literally just going to be whatever voltage we measured on the low voltage side divided by divided by whatever power we measured on the low voltage side, right? So that's going to be 240 volts RMS quantity squared divided by 65 watts comes out to be, so 240 squared over 65 is 886.153 ohms. How would I get this referred over to the high voltage side?
No, you divide. Yeah, low voltage, I think you're right. Divide.
So
Divide by A.
let's figure it out real quick, all right? So A, we don't technically, so we really need to figure out essentially which one we're treating as the primary and which one we're treating as the secondary. So let's say, just for sake of argument here, that we are going to have our high voltage over low voltage ratio will be A. Okay, so essentially we're treating the high voltage side as the secondary and the low voltage side as the primary. So that's going to be, and so in this case, that would be 2400 over 240 is 10. Okay. So going from, and I'm going to make a note up here. So this is secondary, and this is,
Which would mean in this case, we would multiply.
we're going from the primary to the secondary. Yeah, we're going from the primary to the secondary, so we should be multiplying by A squared. So 886.153 ohms times 10 squared is 88.615 kilo ohms. That seems to me like a pretty reasonable value, considering in the previous example that we worked, our core resistance on the primary side or the high voltage side was in the ballpark of 250 kiloamps. So realistically, our core resistance should be tens, if not hundreds of kilo ohms usually. Okay. XM, low voltage. This is going to be a little bit bigger and grosser, right? So let's look back at our equation. Square root of current over voltage quantity squared minus the reciprocal of our resistance squared, okay? So we're going to have the square root of current 6.5 amps over our voltage, 240, square that guy, minus 1 over 886.153 ohms. All of that was underneath the square root sign. Oh, thank you. You're absolutely right. That should be squared. Thank you for that. And so I wound up getting 36.955 ohms when I did that. And I'm going to multiply that by 100. So I'm going to call XM high voltage, is going to be 3.696 kilo ohms. Now we can figure out what RS no, excuse me, REQ high voltage is. So looking back up here just really quickly, our resistance from our short circuit test is just our short circuit power divided by our measured current squared. So that's going to be 300 watts divided by 20.833 amps squared. Zero 0.691 and some change ohms, or 691.222 milliohms, okay, which seems fairly reasonable. And lastly, X EQ S. We're going to get that one. So let's scroll up here. I think it is, yeah. So square root of voltage over current quantity squared minus REQ quantity squared. So square root of our voltage, which was 45. Our current was 20.833. Square this whole thing, minus 0.691 ohms quantity squared. And this comes out to be 2.046 ohms. And we now have the 4 different parameters of our cantilever equivalent circuit. Not going to bother drawing it because we only have 3 minutes left of class. So let's wrap up. Yeah. Yeah, and Sam put her pencil up. So what can I do?
There's something.
Yeah, I'm just shit out of luck. All right. So, oh my goodness. In our next class meeting, we are going to talk about voltage regulation. And that will pretty much be the last topic related to transformers and all of that kind of good stuff. So that will be where the material for exam 1 ends, I believe.
If we have class on Tuesday.
So I would be willing to bet that if the school is closed, we will be told to teach classes online.
Yeah.
So I will be taking all of my notes and shit like that home with me, just in case.
Would you like this?
You can continue to borrow it if you need it.
Yes. Glad you said that.
All right, thank you guys. See you on Tuesday, hopefully either in person or online.